Today on The Future of Everything, the future of semiconductors. Now, semiconductor materials are the basis for most of modern electronics. A semiconductor material is extremely useful because it can be engineered to control the flow of electricity. It can allow it to pass in some circumstances, and in other circumstances, it can stop it or slow it from passing. Very useful for electronics. This ability to behave differently in a controllable way is in contrast to many other materials that either allow electricity to pass freely, like a copper wire or a salt water, or don't let electricity to pass at all, like ceramic or glass or air. So semiconductors are used to create transistors and many other basic elements of electronic circuits that run our computers, our cell phones, communication networks, pretty much anything you plug in or runs on a battery. What's the most famous semiconductor material? Well, it's silicon. With the discovery of how to manipulate silicon in the 50s and around that era, electronics arrived. Now, these discoveries happened at AT&T Bell Labs for the most part in New Jersey, but the center of the industry moved to a region south of San Francisco in the Santa Clara Valley, which became known as Silicon Valley. And that's actually where we're sitting right now. At least that's where I'm sitting. Now, silicon has been a key element in semiconductors for 50 years, but we are starting to run up against some physical limitations in its ability to support electronics. So there's a big push to identify new elements and take advantage of them to provide the next generation of electronics, like phones with 5G, 6G, 7G, faster computers, more efficient computers. Srabanti Chowdhury is a professor of electrical engineering and a fellow at the Precourt Institute for Energy at Stanford University. Srabanti, one of the promising semiconductors is gallium nitride, which I know you work on. What are the advantages of this and other new materials over silicon?
Thanks, Russ. That was a great introduction about semiconductors, as well as, I really am excited about this opportunity to talk about these materials beyond silicon. And as you correctly said, gallium nitride is one of the most promising ones. So the idea is, as you said, in semiconductors, you can control semiconductors to conduct. Sometimes you want them to conduct like a conductor or a metal. Sometimes you want them to stop the flow of electrons or electricity. And the thing is, when we talk about silicon, there are a couple of things that we relate with a semiconductor, such as how much voltage it can block, right? This is when you're talking about a semiconductor in an off state. And I'll introduce a word called switch, okay, early on. So if you think about a switch, which when you turn it on, it conducts, and when you turn it off, it doesn't. Yeah. Now think about that switch made out of a semiconductor, which is our very well-known silicon. Now, when you are looking into silicon, there are certain limitations where how much voltage it can block, okay? And even more importantly, with how little of the semiconductor it can block that voltage. Okay. Mm-hmm. Now, when we talk about silicon reaching a plateau or a limit, we are basically talking about, can we make these switches more power dense, or in other words, can we pack more power per unit volume of the semiconductor? And that's
I didn't realize this. So what you're saying is that you can have a switch made out of silicon that if you could put a big enough electronic voltage across it, it may jump over what's supposed to be a closed switch. And of course, that would limit what you can do because you have to keep the electrical voltages now lower than you might want them for some reason.
Right. The way to look at it, I very much like the mechanical switch that you use to turn on and off your, let's say, the light in your room and things like that. So when it is off, right, it is not conducting. So it's not letting any electricity or current pass. So it has to, in a switch, which as we were just discussing, in that off state, your conduction should go down to zero. And that happens when the voltage across the semiconductor switch is very high, okay? Mm-hmm. And then when you switch it on, you want almost like an instantaneous rise in the current, yes. Or in other words, you want very low resistive loss, okay? Any resistance accounts to loss. So kind of connecting back to the question you asked, like why is gallium nitride is so special? So basically it allows a lot more power dense solution, okay? Like if you look at the trend in power electronics or any electronics, RF electronics, like the radio frequency electronics or computational electronics, the name of the game is how power dense the solution can be, because we want more of it within a very small chip size. We want compact solutions and so on and so forth. So gallium nitride allows things to be more efficient, okay? And I like to think even in another terms, like how less lossy the solution is. Efficiency is a great concept, but sometimes it doesn't strike us what is 99% or 98% efficient. But if you think in terms of loss, then you understand that, okay, if I build a system and if I can reduce the loss from, let's say, 100 watts down to 1 watt, that's a very big thing, right? So gallium nitride allows us to do just that. And it helps us to find out solutions which are power dense. So therefore, you can fit a lot of these transistors, as you very nicely alluded to in the first part, in a very small chip area. And the whole thing actually makes a much more efficient or a low loss solution.
Great. So yeah, so that's easy for all of us to understand, because that means our cell phones get smaller, our monitors get brighter, our computers are more powerful per cubic foot. Now, I know that there are other materials. So gallium nitride, I know people won Nobel Prizes about it, and you can read about it. It seems like it's a very valuable material. But I know that you've also worked with diamond, and I have to ask about that because I love diamonds. And so I just wanted to ask you. So I would have guessed that diamonds were more like glass, that you were not going to pass a current through diamonds, but I might have guessed wrong. So can you tell me a little bit about diamonds in this context?
Thank you for that question. And I love diamond too. Besides being a very shiny stone, it does a lot of good stuff. And you're right, it is what we call insulator, or as you mentioned, the glass is an example. Diamond is an insulator. However, diamond is a semiconductor if you can dope it. That means whenever, as we said, semiconductors, you can control or you can modulate, a little more technical term, the current that passes through this material. Now, that happens because of one very important thing, which is called doping, or in other words, we introduce impurities in a semiconducting material and make it conducting when we want it to. So diamond is a very wide bandgap semiconductor. How wide it is roughly, you can think 2 times wider than gallium nitride. And how wide?
So when you talk about this word of wideness, can you give me a feel for what you mean by a wide or a narrow gap?
Yeah, that's a very good question. So if I try to answer this in a more technical term, I would use two terms here. One is conduction band and valence band. Okay, the distance in energy between these two bands is referred as band gap. The way to look at it is, let's say, if you want to make an electron conducting in a semiconductor, you need to supply a certain amount of energy. And that is roughly equal to this band gap that I'm talking about. So if you supply an electron with roughly the band gap amount of energy, you can upgrade it to the conduction valley, and therefore you can make it conducting, okay? So therefore, if you take silicon, which is sort of our baseline, roughly the band gap is 1.1 electron volt. So you can think about it as a reference. And let's say, with respect to silicon, gallium nitride has 3 times that of the band gap. That means you will need actually more energy to upgrade or uplift this electron to make it conducting. Now, if you take diamond, it's almost 6 times more energy is required. So as you require more and more energy to make these electrons conducting, we call it wider and wider band gap. So coming to your question, so diamond is very attractive because, first of all, it's a single element semiconductor. What is single element? It's made out of carbon, just like we all are. So that makes it fascinating to study the physics in it. And also in terms of the technology and engineering, diamond can be doped. So you can actually introduce these impurities, which did not happen for a very long time. I mean, we were all aware of diamond from periodic table from like long back, maybe from Mendeleev's time, but we didn't know how to dope it to make it into a semiconductor. But now we know how to dope it. Once we know how to dope it, then suddenly we can find out all these exciting things that is possible. And in case of diamond, just to give you a perspective, it can hold 20 megavolts per centimeter. Okay, so if you have a centimeter thick of diamond, you can carry 20 megavolts. I mean, 20 megavolts is still debatable because these materials are so new. We don't know how, these are theoretical predictions. We will understand only with time how much of this can be unlocked or unleashed. But that's a lot of voltage. In other words, in a micron of a semiconductor, you can hold 2000 volts, right? Whereas in case of silicon, for example, that is like 30 volts in 1 micron. So if you hold 30 volts in 1 micron thick silicon, you can think about the picture, you can hold almost 2000 volts in the same amount of the material if you're working with a diamond switch, for instance.
So that sounds absolutely amazing, because any word that has any word with the prefix mega is going to get people's attention, of course. But let me just to check one thing. So you said that these new materials are going to help with efficiency, and yet you're talking about higher powers. So is it the case that they're holding these higher powers, but when they release them or when they allow them to flow, they're dissipating less energy and they're losing less energy, so that the net efficiency is much higher, even though you're dealing with much bigger numbers in terms of the absolute energy that's being used?
That is absolutely correct. So there are two properties which makes a good switch. And again, let's get back to our mechanical switch example. When you're switching it off, you're absolutely disconnecting the circuit, or you're breaking the continuity of the circuit. So that's very ideal, actually, even though it's just sticking on the wall, we don't realize it's a very ideal switch to say the least. Now in the semiconductor, things are not that digital, or in other words, it's not 1 and 0 sort of a thing. So you always, whenever you are in the off state of the switch, or you are not conducting mode, you are slowly leaking current. Okay. And the wider the semiconductor is, the smaller the leakage would be. So that means when the switch is off, if you have no current flowing, then there is no loss. I mean, typically this loss is manifested in terms of heat. Okay, we call it Joule heat. Okay, and that is basically the current dictates how much of this loss will be, how much loss will the switch incur. And if you can reduce this off-state current, you will actually make it very efficient switch. So that is how these wide bandgap materials make very efficient. But the other thing that I said, that another thing is very important in the on state. So this is all a good thing about off state. But in the on state also, when you're conducting, when you're having a high current, it will give you this Joule heat loss, okay, or the conduction loss, I should say. Now, these materials have another very good property. They have very high electron mobility. What is mobility? Let's think about is the velocity of an electron, okay? So electrons move very fast in these materials. So based on these two properties, which a diamond-like semiconductor or gallium nitride semiconductor hosts, we can make very efficient switches.
Okay, that's really helpful. This is The Future of Everything. I'm Russ Altman. I'm speaking with Srabanti Chowdhury, and we're talking about semiconductors and the new materials. So you've kind of actually beautifully made it clear where the benefits of the gallium and maybe the doped diamonds. This is the first time I've heard the word doping in a positive but it all can't be that easy, because you're a professor who's working on this actively. So what are the challenges in the research that need to be overcome so that I can get my faster computers and my better Wi-Fi and all of the, we'll talk about the applications later, but what are the big questions that need to be solved?
Yeah. And that's where all our efforts are going into. So the first and foremost part of any semiconductor engineering is trying to make sure this can be manufactured. Okay, I mean, even though we do a lot of our physics and other exciting science in our labs, ultimately, if you go to an industry guy, he would ask me how much it costs and does it provoke me to change my current solution to this new solution. So the cost is kind of behind all of this, and for those but in order to address the cost, we need to get very high performance. So I like the metric called performance over cost rather than cost alone, because ultimately we pay a lot more money to get a more functional gadget, for instance, right? So we like functions, and functions is sort of derived from more performance. Okay, so to come back to your question, some of the challenges that we need to solve are, how are this manufacturable? Okay, and there's a lot of industry academia relationship that are being fostered currently, which helps us to address this. But in our lab, there is a lot of rich physics. I mean, semiconductors is a lot about physics and a lot of it about engineering. And the beautiful thing is, here we can apply the physics and we can see whether it works or not very quickly. So some of the challenges that we are solving right now is how, when I was describing how less of a loss we can incur during the switching operation, which depends on how high we can dope the semiconductor in the good sense. Okay, and that's one thing, without altering its physical properties and things like that. And also very, very important, can it be scaled, right? I mean, when you talk about a semiconductor, we are talking about 8 inches, 10 inches diameter of wafers, right? So that means that the physics should apply not only to a very little coupon kind of a wafer size, but can it be translated into a more scalable solution? So those are the kind of things we are looking into. So we really care about making this useful, and that's why we really want to focus on finding solutions that can reduce the cost. And believe it or not, it starts with the lab. Like simple experiments. I'll give you an example. In semiconductors, we often use gold-based contact. Okay,
diamonds and gold. This is the best field ever.
Can you believe it? Yeah. So gold we use. By the way, I will make one comment. The diamond that we talk about is a very cheap diamond. I mean, it's called a synthetic diamond. It has a lot of other applications, including jewel industries. Actually, are looking into synthetic diamond, as you would know. But back to the gold topic. Gold is a very common contact metal, but when we were looking into this power electronics, the first thing we wanted to do was, can we get rid of gold because it increases the cost? So, but now it sounds simple, but the physics can completely change if you change the metallurgy, right? So what I'm trying to get at is the ultimate impact of semiconductors, which is in manufacturability or scalability, reducing costs, but all of this have some interesting science that we are solving. So which makes our students very excited about the solutions they're going on. So in our lab, we are looking into trying to make sure we have very ultra low loss switches. Things like, there's a beautiful metric which is called the on resistance of a switch. That means how low resistance can you offer? And there is a metric which we all are targeting, where you can think about that the cooling that you need in electronics can be completely eliminated. So let me take you in one simple example. So for example, if you remember the very early generation of Prius cars, there was no trunk space. And that was because all of that was occupied by the cooling system that was not cooling your engine, but it was cooling just the electronics,
cooling the batteries and whatnot. Yes,
exactly, right? Now if we can build a switch which gives you ultra low on resistance, and then there is a typical number also of that called 1 million centimeters squared, just to quote some fancy numbers here, you can actually eliminate that whole cooling system, so it can be air cooled. Gotcha. So now you can imagine that if you can save that cooling need from electronics, you not only get space, you get a compact solution, and all of this is possible because you have a more efficient semiconductor material.
This is the future of everything. We'll be back. I'm Russ Altman. We'll be back with Srabanti Chowdhury next on Sirius XM with more on semiconductors, new materials, and what they will bring us in electronics and the consumer revolution. Welcome back to The Future of Everything. I'm Russ Altman. I'm speaking with Srabanti Chowdhury of Stanford University about semiconductors and the future of electronics. Okay, so we had a really good discussion and understanding of the basic challenges and promises of these new materials. But a lot of us think, okay, what is this going to be leading to in terms of things that will affect my life? So can you give me a little tour of the types of application areas where you think these new technologies will be making the most impact?
Correct. Yes, that's a great question, Russ. And in the first part, we discussed a lot more about power and power electronics. So I'll focus into another technology that is established and emerging at the same time. So, we are moving from 4G LTE to 5G, and very soon, before we know it, we will be talking about 6G or above, right? So this technology like gallium nitride is a really promising material for delivering high frequency. This is already proved through defense applications where this material is used in radar systems and things like that. But in 5G, or I should say 5G plus, 5G and beyond, those applications, we are looking for very high frequency. You can connect frequency with speed. You can think about higher the frequency, higher the speed. Okay, and that is an easy sort of a concept, as we know that 5G promises greater connectivity, ultra fast connections, or low latency, what we call, right? And also very reliable connections, okay? So all that needs this little transistors to be able to operate at very high frequencies. How high? So current 5Gs are being discussed in the range of 28 gigahertz or to 40 gigahertz, okay? So sub 40 gigahertz. If you're talking about 6G, we will be talking about 95 gigahertz.
So more than twice.
Yeah, right. And so are we talking about, are you doing a lot of the things with silicon currently? Yes, we are still looking into CMOS technologies to serve the 5G, but the improvement in what we call this operating frequency requires the transistors to be way more faster than that, okay? And that cannot be done with silicon. And therefore, we're looking into gallium nitride, and diamond has another interesting role, which is in thermal management. Okay, so we actually integrate in our lab gallium nitride and diamond to make this more power efficient at those frequencies. So 5G will see a lot of applications in 3.5s or gallium nitride and so on, but 6 and above will be impossible without this material. So I think there's a lot of excitement on that. Also, there are other examples like IoTs, smart grid.
IoT is the Internet of Things. So this is where our house is just filled with little internet devices. Our toaster is talking to our refrigerator, and our computer is talking to our front door. This is the IoT.
That's correct. And 5G actually promises what we call massive machine communication. That means all the smart things that you're dealing with, they're all connected to the internet and they're talking to each other. And so this material will play a role not only in the infrastructure or the setting up of this 5G network, but also in the IoTs, because being efficient, they can harvest energy, right?
You don't want a toaster that's costing an arm and a leg to run because it has a supercomputer inside of it. So it really needs to be negligible in terms of the cost of running whatever the appliance is. And certainly if the house is filled with them, you have to make sure that you're not breaking the bank.
That's correct. That is absolutely correct. Cost is, again, they're important, right? So we want to be power efficient at low cost. And again, these materials will play a very big role in that.
Now, I know that you've done a little bit of work in biology, which is an area that we all care about, but I do too. What are the promises in biology as you see it?
Yeah, that's a very, not really a great question, but I would say a very timely one. So how we see that computation in the early decades, computation and electrical engineering, the two came together and made miracles. I think the next decade will see that in many other disciplines, particularly bio. So these materials are chemically inert and biocompatible. Okay, a lot of tests are still in place because as you know, in biology, once you want to implement these things, we have to go through several hurdles. But in a nutshell, these materials, if you can, for example, if you can do a brain implant with this wireless technology where the form factor of the chip is tiny so that it can fit in the cell body of a neuron, for instance, right?
Yes.
So that changes the way brain mapping has been envisioned so far.
Especially if it's not giving out the heat and all those things that you were talking about before. Because right now, an electrode, the problem about putting an electrode in my brain is it might fry my brain. But if you can come up with these more efficient, I could see that being a real game changer in terms of our ability to do implants.
You nailed it. That's exactly the point. So basically, even a 1 degree change in temperature is a lot, right, to our body. So we want to try to see how we can reduce that loss that I was talking there about in terms of in the first part with Joule's loss and all that, Joule heat and all that. So if we can reduce that loss, you can do this brain implant and think about putting thousands of these electrodes because it is reduced in form factor, more efficient, higher frequency, and at the same time, these materials don't add to more heat. So that can be a great game changer. So I'm very excited about bio-integrated electronics for all these reasons.
Yeah, that's very exciting. And of course, in addition to the brain, we have pacemakers and defibrillators for the heart, which currently are quite bulky, and they sit under the skin, and you can imagine all of that getting more powerful, longer lasting. So one quick question and then a longer question. The quick question is, how are we doing? You said that the diamonds are mostly synthetic, so we're going to make those. So we don't care about going to Africa and taking diamonds. But what about gallium? Is gallium in good abundance, or will that be a limiter to the whole enterprise?
Yes, that is in good abundance. So we actually make gallium and combine it with nitrogen in a reactor, which we call growth reactor.
Okay.
This way, not a nuclear reactor. So we do that, and we can synthesize this material, and it's pretty easy. Right now, you can get like gallium nitride in 8-inch wafer size. So it's quite commercial already in terms of the material. Diamond is yet to see that maturity, but the interesting thing about diamond is the way we use methane, which you use for your gas, your cooking ovens, right?
Methane.
Methane gives you, so we strip the carbon out of the methane, which is, we often joke that that's a way we can reduce the carbon footprint as well. But it's a fascinating thing. It's a very cheap way of making diamond, and this diamond is not the quality of the shiny stones as we were discussing. But nonetheless, yes, you don't have to go to Africa to get this diamond.
Great. Now we have about 20 seconds, but I wanted to ask, what kind of team do you have to assemble to make all of this happen?
We really need a team that spans across multiple disciplines and also age. Okay, I mean, right now, semiconductor technology is in its such an exciting stage that we attract a lot of undergrads, even starting from high schools. Okay, there are people who are doing internship in my lab. They're excited about it, and we really want them to know how to build this thing. So that helps a lot when industry cares for it, and also multiple discipline. I mean, the discussion has just begun. I mean, as I was giving the example of computation and electrical engineering, they're doing miracle when it comes to computers. We have to recreate that in bio, in chemical, in other, in sustainability, in the problems that we're dealing with, starting from climate change to, improving the life expectancy, for example, in human beings. All of this can be done with better connection to electronics.
Fantastic. And it all begins with semiconductors. Thank you for listening to The Future of Everything. I'm Russ Altman. If you missed any of this episode, listen anytime on demand with the SiriusXM app.